nuclear fission and nuclear fusion. Little history first. Enrico Fermi, Emilio Segre, and associates bombarded uranium with neutrons in 1934. And remember, neutrons are good because they have no charge and they can get into the nucleus. And they observed beta particles being emitted. That indicated to them that heavier elements than uranium were being formed, which were then decaying and emitting beta particles. Otto Hahn and Fritz Strassmann in 1938 showed that this bombardment resulted in the formation of barium, which was a heavy nucleus but still less massive than uranium, which confused people at the time. Then in 1939, Lisa Meitner and Otto Frisch found that uranium was actually undergoing a fission process. And fission just means breaking into smaller things. And in this case, smaller particles, which were roughly the same size, like barium and krypton, were being formed. These particles would then decay via the beta particle emission, which was observed up here by Fermi and Segre, and that's what they were observing back here in 1934. Slow neutrons, or thermal neutrons as they're called, were better at producing this nuclear fission. Here's a neutron right up here, and here's a U-235, uranium with a mass of 235, because the combination of their neutral charge and low energy allowed them to stay closer to the nucleus for a longer period of time. When that happens, the thermal neutron becomes part of the nucleus. The nucleus grows just a little bit so that some of the nucleons are outside the range of the strong nuclear force. The nucleus will stretch out until finally it splits apart or fissions. And here's one particle, here's the other particle, here's the other nucleus. You can see these are roughly the same size. They're smaller than the uranium. And look at here, we have 3 neutrons coming out, and they can then hit other uranium-235 nuclei and continue this fission process. This stretching of the nucleus has a name. It's called the liquid drop model. From the previous slide, we saw how the target nucleus, which in this case was uranium-235, fissioned or split into 2 nuclei of smaller masses and a few extra neutrons. The general equation for the fission of uranium-235 plus a neutron, yields uranium-236. Remember, this thermal neutron became part of this nucleus, so it's now uranium-236, and it's in an excited state, that's the asterisk. It produces 2 nuclei, plus neutrons, plus energy. And this is the whole point of a nuclear fission reaction, to produce energy. Q is the energy released. Many different combinations of X and Y are possible. Here's a couple of examples. We have uranium plus a neutron gives you an excited uranium-236 nucleus. In this case, you get barium and krypton and 3 neutrons. In this case, you get xenon and strontium, and you only get 2 neutrons, and again, you have the energy. So the key point, you have energy released and you have more neutrons released that can then go find another uranium-235 nucleus and continue the process. The energy release in a fission reaction is quite large. The smaller nuclei are stable with fewer neutrons, and we showed that curve earlier where we plotted neutron number versus proton number. The bigger nuclei need more neutrons to keep them together. So now that we have smaller, and here we have these smaller nuclei coming out, they need less neutrons to be stable, so they get ejected from the reaction. And you can see how this neutron has found another uranium-235 nucleus, which then fissions, which releases more neutrons. This is called a chain reaction. Enrico Fermi built the first self-sustaining nuclear reaction in Chicago in 1942. And you can click on this here and see a very nice simulation of what a nuclear reaction looks like, what the fission process looks like, what a chain reaction looks like. This process is used in nuclear reactors throughout the world. And here's a basic schematic of a nuclear power plant. We've got the core here, And right here is where you have the uranium, where you have your chain reaction, where you have uranium-235 being struck by neutrons and releasing quite a bit of energy. And what are we doing with that energy? It goes through a primary coolant system, which is water, which is kept at a very, very high pressure, so it can get to a very high temperature without boiling. It can be up to about 480 degrees Fahrenheit and still be water because it's under such a high pressure. This water goes into another tank here, a pressurizer tank, and then it just circulates this water around here. Well, if that's all it did, we wouldn't be getting too much energy, useful energy out of it. But we have a secondary loop here, where we have other water going through here, being heated by this very hot 480 degree water, coming through, and then turning into steam, because it's not under such a high pressure. And then we have the steam hitting a turbine. So basically, we are just doing the same thing that a normal coal-fired plant, gas-fired plant. We're boiling water on this side to make steam. It hits the turbine blades, they spin, they generate electricity. So really, a nuclear reactor is almost like a big, just a heat source for a tea kettle here, to boil water, turn it into steam, make a turbine spin, and then create electricity. And the reason you have these two loops, we have the one loop of water here, this stays close to the reactor, so any radiation that's being caused stays within this containment building, and we have water over here that is not radioactive in any way, and that is what is driving our turbine plant to create the electricity. The nuclear reactor is controlled by regulating how many neutrons. That's the key part. You saw how when uranium-235 is struck by a neutron, it will fission, producing fission products like barium, krypton, and more neutrons. So depending on how many neutrons we let hit other uranium nuclei, that tells you how fast the reaction will proceed. So there are objects called cadmium and boron control rods which will absorb neutrons. They are carefully adjusted to absorb just the right amount of neutrons to allow a self-sustained, controlled chain reaction. They don't let it get too big, or else then you'd have trouble. They don't let it get too small, or you wouldn't get the water hot enough. So it's very carefully adjusted, these rods, to absorb just the right amount of neutrons. Another definition is critical mass. That is the mass of fissionable material that is required for nuclear fission to occur. You can kind of visualize if the uranium was too spread out or you didn't have enough of it, the neutrons, when they were ejected from the first reaction, may not find another uranium nucleus, so the reaction would not keep going. So you need a certain amount of mass in a certain small amount of space to keep this reaction going. Nuclear reactors are designed with layers upon layers of safety and security features. And the physics behind it, the way it's arranged, the way it's engineered, there's no possible way for a reactor to ever cause a nuclear explosion. It just can't happen. Nuclear weapons are designed totally different to explode in a massively uncontrolled chain reaction. You can see here's the word here, uncontrolled. And they are very, very different from a nuclear reactor. Nuclear fission worked by splitting uranium into smaller nuclei, releasing neutrons, starting a chain reaction, and giving up a whole lot of energy. The other side is nuclear fusion, and fusion means you put things together. In 1938, Hans Bethe postulated that the reason the sun doesn't cool down, despite the massive amounts of energy it was releasing, is due to nuclear fusion. Now, uranium is a very, very heavy element. Nuclear fusion, on the other hand, is the combining of two lighter nuclei to form a larger nucleus, which results in the release of more energy than was put into the reaction. This occurs for elements on the first part of the binding energy nucleon chart, which has a positive slope. That was showed earlier in this unit, where we had curves up like this, and then up here is iron and nickel, and then it comes down, we have a negative slope, and helium is somewhere in here with its peak. So we have this line here. To the left, elements on the left are more likely to undergo fusion, and now on the right it's fission. And that's because the heavier elements formed have a greater binding energy per nucleon, which implies a decrease in mass, hence a release of energy. So on this side of the binding energy per nucleon curve we have fusion reactions, and on this side we have fission reactions. Here's what happens in our sun. It's nuclear fusion. It starts with 2 hydrogen nuclei, puts them together, gets deuterium, that's an isotope of hydrogen, releases a positron and a neutrino. Now, and that reaction there releases 0.42 MeV. Then another hydrogen combines with the deuterium that was made here. Let's put that just to show the connection. It now forms it forms helium, an isotope of helium with mass 3, and a gamma ray comes out. This is released 5.49 MeV per reaction. Now, 2 of these helium nuclei are combined. They form helium with the normal isotope of helium with the mass of 4, and 2 hydrogen nuclei, and that releases 12.86 MeV. So we started this process with 2 hydrogens, and at the end we wound up with this helium here, and we have 2 more hydrogens ready to go to start a new reaction. The final balanced reaction shows we've transformed 4 protons into a helium nucleus plus 2 positrons, 2 neutrinos, and 2 gamma rays. Very massive stars can create elements all the way up to iron via the fusion process. Elements heavier than iron are only created in supernova explosions, as they require more energy put into the reaction than is released in the fusion reaction. So all the elements in our body that are heavier than iron were created in star explosions, supernova explosions. So we really are made of star stuff. Nuclear fusion requires an incredible amount of energy to start the reaction. In the sun, this energy comes from the high temperatures and pressures found in the core of the sun. This causes a plasma. That's the 4th state of matter, where atoms are highly ionized and electrons are separated from their nuclei to form, which facilitates the reaction. So if we wanted to do that on Earth, that would be great, because a nuclear fusion reactor would have great advantages over a fission reactor. Its fuel, hydrogen isotopes, deuterium and tritium, are far more plentiful than uranium-235, and a fusion reactor produces far less radioactive waste. So given the great advantages of a fusion reactor over a fission reactor, why don't we have them now? It seems they make a lot of sense. The problem is we have to put more energy into it than we get out. It's an engineering issue. We need physical containers to control the high temperature plasma in which the nuclear fusion will take place. Problem is, any physical container we come up with will melt. So physicists and engineers for decades now have been trying to use magnetic fields to control the plasma. And they can. They can control the plasma, keep it contained. However, the creation of these magnetic fields requires so much energy that, once again, we're putting more energy in than we get out, so it is not a viable energy source at this time.